And hello, YouTube. We're back. All right, what are we doing today?
Can we all say it on three?
What are we doing today? What is a slope field? Well, we've talked about this a little bit, but kindly consider the following. Let's see. What if dy dx is x? Can you draw me a slope field for that? Yeah, how do you draw a slope field?
It's just like the lines.
Yeah, what you do is you make like a little lattice. Little lattice structure. Sounds like chemistry. Okay? In other words, give me a point here, 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 and so forth. Maybe a little over here, over here, over here. And what I'm going to do is going to sample these points and put them, let's say this is -2, this is the origin, this is +2, this is +2. Put these points into your DiffEqu and see what the slopes of the tangent lines look like. So you can draw little mini tangent line slopes, little line segments, and you could actually get a feel for what the solution curve looks like by following those slopes. So, what if I plugged in this point right here? What's this point right here? -2, -2. All right, so dy dx is -2 because x was -2, yes? Notice the slope field here only depends on what the x value is. Aren't the x values here all -2 on this vertical line? So a slope of -2 would be pretty steep negative, say? What about at x equals -1?
A little less steep.
A little less steep, but still negative. How about at x equals 0? 0 slope. How about at x equals +1? Positive slope. And +2, a little bit steeper. And you can keep on doing this with a whole bunch of points. But if you draw a curve through the point, say, I don't know, 0, 0, that follow these slope lines, what would you get? What kind of graph? This is parabolic, isn't it? Look, separate it. dy equals what? X dx. Integralize. Sorry, YouTube. That's not a real word. I'm not supposed to say integralize on YouTube. All right, so y is what? Go ahead. X squared over 2 plus a constant. Now, how do you resolve the constant? Well, it depends where you start. I started at 0, 0. So plug in 0 for x and 0 for y, and what's a got to be?
It's gotta be
0. So it is a parabola, isn't it?
Yeah.
Aha. Can you generate the same slope field on a calculator?
yeah.
If you had to. What if it wasn't so easy? All right, let's see. Let's get a calculator out.
Whip it out.
Where is it? Where is it? Where is it? Here it is. Let's put the same slope field in here. Now, I think, though, be careful. You have y1 prime, y2 prime, y3 prime, right, of t. Because a lot of times what we're modeling is a function over time, like a population growth model or something. So the variables here are y1 or y2 or y3 with respect to t. So let's see if we can graph this thing. Instead of dy dx equals x, I'm going to do dy dt equals t. All right, same idea. So new document, and it's a graph. And, well, let's change the mode. Menu. Now I forget how you do this now. Graph entry. Is it graph entry? 3? There you go. So DiffEqu is 7. Do you see it?
Sure.
All right, so 3, 7. And y prime, now notice it's y1, you can have y1 prime, y2 prime, y3 prime, but they're all functions of t, because ahead of time the calculator doesn't know that you have a function in x or whatever it is. So, all right, so instead of dy dx equals x, I'm going to have dy dt equals t. Is that okay? All right, so get rid of that. So t. And where's the t? There it is. Alrighty, so enter that. And what happened? Nothing. Oh, wait, it is an x, though. Okay. Interesting. All right, so let's go back to where we were. Let's make it... all right. Did I write a t there? Yes, I did. All right, how about if I write an x? Maybe it is an x. I'm thinking of the 89 where everything was in terms of t at this point, but let's see. Oh, there you go. Okay. Does that look like, sort of like what we drew? Parabolic? Now, it's sampling different points depending on the size of your x min, x max, y min, y max, and the resolution of the screen. You're going to be sampling points at different locations than what we had. But is that parabolic? Now, what if you wanted to draw the solution curve? Let's see. go back to y1. Notice what it says down here. You can give it an initial condition. Now, what did we do? 0, 0? Yes? Okay, so 0, 0. And there you go. So there's your, supposedly, x squared over 2. Y equals x squared over 2. Is that good? All right, so I take that back. These are not functions of t. These are functions of x. I'm thinking the T89 did that. The 89 and the nSpire are almost identical as far as software is concerned. So that's unusual, but there you go. All right, questions how that works. Can you do slope fields by hand? A lot of times this doesn't happen to be that useful because a lot of times you're going to get slope fields on the non-calculator active section, and either they draw it for you or they're going to ask you to draw it by hand. So let's try another one. Are we okay?
Yeah.
Are we stuck?
What's the purpose of this?
Well, this is a nice way to solve differential equations or get a feel for the solution of differential equation if you can't actually integrate it. Now this one, I could integrate it and see that the slope field makes sense. But what if it's something that's hard to integrate or impossible to integrate?
Yeah.
There are several integrands that don't have closed form analytic algebraic solutions. So you have to do it graphically or numerically. This is a graphical approach. All right, let's see. Tomorrow we'll talk about a numerical approach called Euler's method. What if I said dy dx is y? Okay. All right, so again, let's make a little lattice here. These points here. I like these points. It doesn't have to be these points. A lot of times they'll give you, on the free response section, they'll give you a bunch of points like this to fill in. All right, now this one's also easy in that dy dx, the slopes all depend on simply y. So what is the y value up here? Say, let me start here again.
2.
It's 2. So this whole horizontal line here at y equals 2, the slopes are all going to be the same, right? So slope of positive 2 is pretty steep. How about at y equals 1?
1.
A little less steep. How about y equals 0?
0.
Really less steep? Okay, let's make this maybe a different color. Hello? It's not letting me do that? Okay, fine, thank you. I'll do it this way. Of course not. What did you just do? It's still red. Hey! I'm going to make it blue. No, I'm not. It's blue, right?
It is blue. No, it is blue. It is blue.
You just
Now
looked
it's
at the
blue.
color one, let me see.
It's blue. No, it's blue.
That's blue? Okay, YouTube are having technical difficulties, but here we go.
Yep.
So here's all. All right. So what if we started at y at the point 0, 1, and I tried to graph solution cursor here? Does this look familiar? It's probably something exponential. Yes. All right, and it's got to be because can't you solve this by variable separable? So you do this when you can't do that. But I'm giving you an example you can do both ways so you can corroborate your solution, right? So separate. What do you do? dy equals y dx. Is that integrable?
Yeah.
No, because the y and the dx you can't integrate.
So they should divide by y.
Okay, put the y's with the dy's and x's with the dx's, then integrate such that dy is in the numerator and dx is in the numerator.
And you get 1 over
What is the, yes, 1 over u du, what's the antiderivative?
ln
ln of y. All right, so the ln of absolute y is equal to what? X plus a constant, right? Okay, can we get rid of the ln? I want to get y alone if I can. E to the both sides, and you get
e to the x plus
y equals, well, let's do it this way, b e to the x. Now, I went through the point 0, 1, right? When x is 0, y is 1, or y of 0 is 1. So, what's b? Plug in y is? Nope.
1.
1. And x is?
0.
And e to the 0 is usually?
1.
1 times b is?
1. B.
B, so b is 1. All right, so y is e to the x. So you're right. It was e to the x. All right, take a look at this worksheet from the Harvard Calculus textbook. We're in section 11.2, slope fields. Giving credit where credit is due. I like this, how they do DiffEqus in this book. I'm using this for this week.
It's easier to understand.
Yeah, okay, yeah. This is the book they use in the summer. They teach Nassau. I guess lecture in the summer. All right, so take a look at number 9.
I believe there's a.
You got the multiples of 5 tonight for homework.
Oh, good?
Yep. Right? Worksheet 11-2. Multiples of 2, actually. Because I think we've actually talked about this before. I think I gave you this
Yes.
some time ago. We did 5s and 4s already, believe it or not. So 2, don't do the 4s. We did the 4s. So 2,
4,
not 4,
Six.
6, not 8,
10.
10. Okay. Alrighty. So that was our arithmetic lesson for today. All right, good. All right, number 9. The subfield for y prime is x plus y. This is page 595, 6th edition Harvard textbook. This is question number 9. Okay. All right, that subfield is given, but we could generate it on the calculator if we need it. And all right, see it? Do you see it right down there at the bottom? What if we drew a subfield through 0, 0? Maybe we should generate this on the calculator. Let's see. Let's get the calculator involved. Where are your calculating device? All right, so let's go to y1. Go back. Yeah, really? Why isn't it going up? Yellow. My documents, my unsaved document. Go to y1. There you go. All right, let's change it. Now, what do they want? They want x plus y. Okay. So x plus y. Where are you? There it is, next to the x. Yeah, that would make sense. And what happened? Oh, what I do? I did what I told you not to do. What's wrong with that?
Whoa.
There's only 2 variables here, x and y1.
The homework
Right?
is drawing.
Where over here, it's y1. If you ever reference y over here, it's y1. If you're on this in the y2 line, it's y2, right? So bad teacher, bad teacher. Well, look at that. Well, we answered question 1A, did we? So 1A was what happens if you go through 0, 0. But the idea is, what could you draw that by hand? Would you have gotten that by hand? Notice what's going on here. We have sort of like there's a solution here that's sort of linear, it looks like, yes? If you start here, it stays on a line, sort of, right? But if you're above that, it does craziness. If you're below that, it does this kind of craziness, right? So that's what this question is all about. What if you start at 0, 0? Okay, so it's a little bit above this line. There he goes. What if you start at negative 3, 1? All right, negative 3, 1 is here. So it's a little bit below that line. Can I draw on this thing? I don't know if I can. Of course not. Give me an ink layer. Whenever I want an ink layer, I don't get it. Okay. Well, it's going like this. Say. Doing that. All right, so let's see. Let's see if we can get that from here. The idea, can you draw that? Draw it. Go ahead. Draw it.
Does that have to be exactly accurate?
No,
It could be
close.
like a general sketch.
Right, so 3, 1. Make sure it goes 3, 1, and it's doing asymptotic to this slant asymptote here, and then it's going down to like negative infinity. Okay? So YouTube, I'm doing this. Something like this. Okay? Can we show that on here? Let's see. What if I go back up here and change the initial conditions to, instead of 0, 0, it's going to be negative 3, 1. Okay. You got me. You got me. You got me. All right, let's change the initial condition to negative 3, 1, right? Okay, let's see if that is what we expected. So negative 3 here, and a 1 here, and go. So like we said, asymptotic, if as x goes to negative infinity, going asymptotically to that slanted line, and as x goes to positive infinity, it's going to negative infinity. Okay, good. And you could have sort of sketched that by hand, right? On the paper. Just do that. But then what if you started negative 1, 0? What if you started negative 1, 0? Isn't that sort of like on that? I think that's on the slanted asymptote that we're getting. So if you start there, you're stuck there. So there's 3 distinct kinds of solutions here. Right? The one that goes off to positive infinity, the one that goes off to negative infinity, and there's this linear one in between. Sort of like a boundary. Yes? All right, so question B. From your sketch, write the equation of the solution passing through negative 1, 0. Well, it's going through negative 1, 0. And if you plug in negative 1, 0 here, what's the slope? So you want a line that goes through negative 1, 0 with a slope of -1, right? This guy right here. So can you write the line? That's all they're asking for. So how do you write the equation of the line? Y minus y1 equals m times x minus x1. So what's y1? 0. What's m? -1. And what's x1? So minus a -1 is a +1. And if you distribute, y is going to be a -x minus 1. So is that what we had? Right? So if we had y equals -x minus 1, we have a -1 slope and a -1 y-intercept. Yeah, that line right there. Going like this. Okay. Alrighty. And part C, check that the solution makes sense. How do you check the solution to a differential equation? Have we ever done that?
No.
Well, actually, it's very easy. How do you usually check equations? That's, what is this? This is not an eraser. Okay, this is an eraser, okay? Fine. Da, 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 da. Okay. What is going on? Why? Okay, that's great. Okay, thank you. Alrighty. YouTube, you saw nothing. Okay. So how do you solve, when you solve an equation, how do you check it? You plug it back in, right? But the solution here is a function. So plug the whole function back in. In place of y, you're going to write -x minus 1. And in place of y prime, you're going to write, well, what is y prime? -1. So is -1 equal to x plus -x minus 1? That's the question. Check. It's always a question. Yeah, the x's cancel, and does -1 equal -1? Checkola. There you go. That's what it's called. Check cancels the question mark. All right, is this terrible? So this is the kinds of questions you're going to see in the homework, all right? So multiples of the evens today. How about, any questions number 9? We good? How about 13? Okay, 13 says, the slope field for the equation dp/dt, okay, so this is 13. dp/dt, or p prime, is 0.1 p times 10 minus p. Okay. For p is greater than or equal to 0. So that diagram up there in the corner, top hand, right hand corner. Sketch solution curves for 0, 0, 1, 4, 4, 1, and so forth. And well, we'll get to that. Now look at the slope field. Do you see some equilibrium solutions? When is p prime 0, in other words? We talked about equilibrium, didn't we? In the past? We have, but you don't remember. That's when the growth rate is 0. So dp/dt is 0 when? When p is 0, or when p is 10. Now look at the slope field. Does it look like at p equals 0 you have horizontal slope lines? And at p equals 10 you have something going on horizontal. It's hard to tell because it doesn't hit 10 exactly, but it's getting close, right? What if we put that in the calculator? Let's see what it looks like on the calculator. Let's see, so let's go back to here, or not, again with this. There you go. All right, so let's change it. Now, notice, I'm in the y1 prime line. So there's only two variables here, y1 and x. But I want to write this. So who's y and who's x? P, well, I'm thinking the y dx is 0.1 y 10 minus y. I'm thinking the dx on the bottom. Right? Okay, so now it's y1 on the calculator. So that's what you got to write. 0.1 times y1 times 10 minus y1. Okay, let's do it. So 0.1 or 0.1 times y1, just in case there's an implicit multiply issue here, I'm going to multiply explicitly, times, well, the parentheses should probably obviate that, but here we go, 10 minus y1. And let's see what that looks like. Okay, and I put an initial condition here. I don't want that. So tab up. Get rid of the initial condition for a minute. Can I just do a clear? No, I cleared the wrong thing. Really? I'm not on that line. Why are you clearing that line, you dumb computer, you? Okay, me and Casper get along, you can tell. Let's try this again. Did I do that? Right? And of course, it wants the times. Like I said, didn't I say it? I said it. But there should be, oh no, there it is now, because then it thinks it's y1 of a function value or something, right? So that's a problem too. All right, now, look at your slope field that they gave you. They're letting p go from 0 to 10. Do we have that here? No. So let's change our window. I guess 4. All right, now, negative 10 to 10 for x is okay, but it's the y's that we're not getting. Okay, so negative y is fine. I need a bigger y max, bigger than 10, so you can see what happens at 10. How about what? 15? Okay. Not going to be a square window, but that's okay. And there you go. So you're getting what they sort of showed you on the page. Horizontal slopes at p equals 0, y equals 0, and horizontal slopes at p equals 10, or y1 equals 10. All right, so those are the equilibrium solutions. Now, if you take a look at the equation, if you pick a value between 0 and 10, say 5, what's the sign of p prime? Say you plug in 5 for p. Is this positive or negative? Positive. So that's why you see growth, right? There's growth going on here. But as it gets closer and closer and closer to p equals 10, it starts to level off. Because if p is 1, this is 9. That's huge. If p is 5, this is 5. This is less huge. If p is like 8, this is 2. That's even less huger, right? Is this English? All right. So if p is like 9.8, this is only 0.2. It gets really, really small. It's still positive, but it gets really, really small. So you see why it levels off? It's going up and then it levels off. It's almost like an exponential approach. And an exponential decay over here too, as you get p is closer and closer to 0. But the growth rate is greatest somewhere in the middle, somewhere between 0 and 10, 5. Right? Do you see what's going on here? What's changing here in the slope? If you graph this curve, what's changing here?
The
Concavity, right? So if you found y double prime, the second derivative, and set it equal to 0, you're going to find that the maximum growth rate of this curve occurs at half the carrying capacity. What? This is the carrying capacity right here. It never goes above 10, does it? If you start somewhere between 0 and 10, you're never going to go above 10 because of that equilibrium point. Now, is y equal 10 or p equal 10, is that a stable or unstable equilibrium? Remember, we talked about this.
Unstable.
That's stable because we're trying to get to it. Whether you start above or below, you're trying to get to it. But what about p equals 0? Is that stable or unstable? That's unstable because as t increases or x increases, the y values are going away from 0. They're going away from 0, right? All right, so we can answer the question. What happens if we start at 0, 0? This is question A, 13A. 13AI, oh my God. So if you start at 0, 0, what's your growth rate? 0. So the horizontal line is the solution, yes?
Yeah.
Okay. What if we start at 1, 4? 1, 4. Say here. What happens?
4 looks like a positive something.
You're going to get that weird changing concavity thing?
Yeah.
With that curve, we call that a logistic growth curve. A lot of times you model populations with exponential growth, right? So, but the populations really go to infinity? No, that would be bad. That's called a doomsday solution. If your solution includes like 2 to the x as the answer, that's doomsday solution because you're going to run out of resources. You're going to die out. And you could have exponential decay too. That would be bad too, right? But this is sort of both. It's like decaying this way and approaching this way. So instead of going off to infinity, it levels off to something. That's more a more realistic population growth model. It's used a lot in biology, logistic growth. All right, so this equation, this is a logistic growth model. And this slope field is a logistic growth slope field. And your solution, well, let's see. What if we put in, what is it, 1, 4 they want? Whoops, not that. Here we go. Let's put in, they're doing that again. Jeez. Okay, go up here. Let's put in the 1, 4, see what we get, what we're saying. And there you go. So if you start at 1, 4, it's graphing this one, it's graphing this one, so you can see the whole logistic curve. Okay? So you can solve all kinds of differential equations with variable separable. Some of them can't be integrated. You can solve a whole bunch more this way. Okay? At least numerically, graphically. But there's 3 main types of DiffEqus that come up a lot on the AP. You know what? In fact, let me write it this way. Can I do that? No, of course not. Stop it. The PDT is, I don't know, P. The PDT is negative P. Do you recognize this? The rate of growth of your population is directly proportional to the population you have right now?
Yes.
Does this sound familiar? Or directly proportional to with a negative growth rate? Yes? What is that? What does that look like? Well, didn't we just solve one like this?
Oh, it's like
That's exponential. Didn't we just do dy dx equals y? It's exponential growth. So this is exponential growth or decay. That's the kind of thing you're going to get, right? You might also see this. The PDT is directly proportional to, let me think about this. Is it P, 1 minus P, let's say. 1 minus P. All right, or negative 1 minus P, something like that. Now, think of it. When is the growth rate 0? On this one, on the top. When P is 1. Okay. So say this is P equals 1. What happens if you pick a number between 0 and 1, let's say, to start as your initial condition? So you plug in a half, and K is positive. What's happening? If we plug in a half and K is positive, what's this? Positive or negative? Positive. The whole thing is positive, right? But as you get closer and closer to 1, plug in 7. This is smaller. Plug in 0.8. This is smaller. Plug in 0.9. This is smaller. It's doing this. What if you start with P is greater than 1, say 2? And it's going to look like this. This is called exponential approach. Not exponential decay because it's not going to 0. Or right? It's sort of decaying, but it's decaying to something other than 0, so we give it a different name. But then, so you have exponential growth, you have exponential approach, and you have logistic growth. Now when is the PDT 0? What do you plug in for P to get P prime is 0?
When the second
0 or 1, right? So 0 or 1. And that's when you get this logistic growth stuff, like this. If you take a look at the slope field that we had, where is it? When you're less than 0, it's just, I don't know what the heck you would call this. This is going to negative infinity here. When it's more than the carrying capacity, in this case it was 10, it's decaying. It's like an exponential approach. So you're getting solutions that look like this, or like this, when you're outside the range 0 to 1. Okay? That's a logistic growth model. If it's negative, what would it look like?
opposite.
It would be, well, I can't do blue. You know, yeah, I have the eraser on. I'm still writing. This is great. Okay, so do this. Do you see it? We'd do this, negative slopes, and then this would be positive slopes. And this would be positive slopes. All right. Anyway, so you have logistic growth and decay. You have exponential approach from above or below. And you have exponential growth and decay. Okay? These models come up over and over and over again in nature and in science and biology and physics and whatnot. They come up on the AP exam all over the place. All right. So, did we answer the question? Let's see. This is still 13, right? So we know what happens if we go through 0, 0. We know what happens if we go through 1, 4. What happens if we go through 4, 0, 4, 1? Can you draw it on the paper? let's see, 4 for t, 1 for p, and draw the solution curve. What does it look like? It looks like this curve except shifted, right? So instead of going through 1, 4, we're going through 4, 1. It's doing it over here. It's going to be doing the changing concavity over here. But notice the changing concavity is always halfway between the two equilibria. Okay. What about negative 5, 1? Negative 5, 1 here. Isn't it the same shape? Just shift it over? Okay, good. How about negative 2, 12? Negative 2, 12 up here.
There's a different solution.
That's right. So that's going to be exponential approach to y equals 10, I guess it was, or p equals 10. And what about negative 2, 10? Negative 2, 10, right here. That's a zero growth rate, so it's stuck there, right? So you really have these solutions up here. You have these logistic solutions in the middle. You have these solutions down here. But this is a solution also. Y equals 0 and y equals 10. So there's really 5 different kinds of solutions here. And guess how you solve these kinds of DiffEqs? Well, look at it. Not that. Where is it? There it is. How would you variable separate this? Oh, I can't erase, so forget it. Okay, how would you variable separate that? All right, let's go somewhere.
dy equals
You got dp dt is 0.1 p 10 minus p, right? All right, so what would you do?
dp equals
All right, Justina, what were we saying? What were we going to do first?
no, I didn't say.
No, you didn't say nothing. Okay, what'd you say?
So you're going to move the DC equals
Move the dt up,
divide by that.
but you got to divide by the p, so it goes with the dp. So dp over p times 10 minus p is equal to 0.1 dt. If you integral, can I do that? Jeez. 0.1 dt. If you take the integral of both sides, this is easy. 0.1 what? C plus c, right? But this, how do you take the integral of that? Oh, is it an ln though? But is it?
Can't use the product rule?
It's not a product. Look at it. It's not a product. By part? No, not by. That's product. What do you mean? You don't mean by part? The other one. Not by part. By parts is a product rule.
The fractions are
The partial fractions rule. Yes, this is partial. This is where partial fractions comes up all over the place. Okay, so guess what? They're going to give you equations like this to solve on the AP free response section, probably somewhere, if they want you to do a partial fractions integral someplace. So yeah, we're going to practice that up, but not today. Today we're just focusing on the slope field stuff. Tomorrow, that's a graphical approach to solving differential equations. Maybe you can't solve any other way. Tomorrow and the next day, we're going to write a program. We're going to talk about writing a program to solve these things numerically so that you get these solutions. You get the points along the curve. You can get any point along the curve using this method called Euler's method. We're going to talk about that for the next couple of days. And then on Friday, we'll just refresh your memory that which solutions you can actually do analytically by anti-differentiating. So this is today and tomorrow is mainly about what if you can't anti-differentiate? Is there something else you can do? Right? Okay, and my throat is killing me, so I'm done. All right. So see ya.
Bye,
See you,
YouTube.
YouTube. Have a nice day. Bye-bye.